Okay, section 3.1, number 35. And number 35, we are trying to locate the absolute extrema of the function on the closed interval. Our closed interval is 0 to 1/6. Our function is cosine of pi x. So, first thing that we look at is we say, hey, cosine is a continuous function. We are taking it's a composition of pi x is also continuous. So this is definitely a continuous function. And furthermore, it's also a differentiable function. We can see that because we know that from the graph of cosine, right, there are no sharp turns or anything in the graph of cosine. There's no sharp changes in its rate of change. I can also just take a derivative and see that I don't run into any problems with the domain of the derivative. So for example, if I were to take the derivative here, I would get the derivative of cosine is negative sine. And since this isn't just of x, it's of some function pi x, I need to take the derivative of pi x, which is just pi. So this is what its derivative is, and you can see that sine is also a nice function that's defined pretty much everywhere. So it's also differentiable. I don't actually think that that is a requirement of finding the intervals. All we require is that it is a continuous function. But we've also answered one of the questions, which is finding where the derivative does not exist, and the derivative exists at all points for all values of x. I can put in some number here and get out a value for its derivative, and it doesn't matter what that x value is. It's defined everywhere. So that's good. So the question becomes, where is this function equal to 0 for determining what the critical points are? So what we do is we say negative sine of pi x. Where is that function times pi equal to 0? And the answer to this is many places, right? Let's make it a little bit simpler here. This is like saying multiply both sides by a -1. Well, so 0 times -1 is 0. Divide through by pi. 0 over pi is still just 0. So we get sine of pi x equals to 0. So where is sine of pi x equal to 0? Well, we can also take the inverse sine of both sides, and I get pi x. And it's like saying, one thing that we're going to use a loose definition of the inverse sine here. Let's pretend that this is saying wherever sine is 0. So if we take a look at a graph of the sine of x on an interval from 0 to 2 pi, on an interval from 0 to 2 pi, we have that sine is 0 here, it is 0 here, and it is 0 here. So we have at least 3 locations. But if we were to zoom out and instead of 2 pi we were to use 4 pi, we would see that this is another cycle of sine, or another period of sine. So we get another 0 here and another 0 here, and it would just continue repeating. It also continues to repeat in the other direction as well. Our first 0 is at 0 itself. Our next 0 is at a value of pi greater than that. And then our next 0 is at a value of pi greater than that. And our next 0 is at a value of pi greater than that. So if we were going to come up with a description, and since there's infinitely many of these points, we would want to come up with a way of describing it algebraically so that I didn't have to enumerate the list of every single value where sign of 0 is 0. It occurs wherever we get a value of a multiple of pi, right? 1 pi, 2 pi, 0 pi, 3 pi, negative 1 pi, so on and so forth on either end. So one way of putting that is that wherever I have n pi, where n is an integer, the mathematical way of writing that is n in z, and z is our method of describing integers. And that's wherever pi times x is equal to n times pi, where n is an integer. So I can divide through by x here, and I can see that x equal to n. So that tells me that I have a critical point at every single integer. Okay, so now what we have to say is where do I have a integer value in this interval of 0 to 6, or 0 to 1/6, to identify where a critical point might lie inside of this interval. Well, I have 0, my next integer after that is 1, and my integer before that is negative 1, so the only actual integer value that occurs in this interval from 0 to 1/6 is at 0. So 0 ends up being a critical point. It is both an endpoint and a critical point. So this tells me that my value of this function can attain a min or a max only at its two endpoints. And since it's a continuous function, one of them is the min and one of them is the max. So let's just evaluate it. So f of 0 is cosine of pi times 0, which is equal to cosine of 0, which is 1. F of 1/6 is cosine of pi over 6, and we know that this is a reference angle. If you have your reference angles memorized in terms of degrees, right? This is pi over 6 times 180 over pi degrees, which makes it 30 there. So this is 30 degrees. If I think of my reference angles, I always make this cool looking chart. I have sine and cosine, and these are my angles: 0, 30, 45, 60, and 90. And it goes from 0, 1, 2, 3, 4, 4, 3, 2, 1, 0, and divide everything by 2. 2, and square root the top. Theta, theta, and these are different reference angles for theta. And so this is pi over 6 right here in terms of radians, and it will be equal to square root 3 over 2. Square root 3 over 2. Okay, so my one endpoint is 1. My next endpoint is square root 3 over 2. What's square root 3 over 2 when compared with 1? Well, square root of 4 is 2 itself, right? So square root of 3 has to be a little bit less than that. So we have something slightly less than 2 over 2. So that means that this is going to be less than 1. So this means that this guy here is my max value, which occurs at x equal to 0. And this guy right here is my min value, which occurs at x equal to 1/6. If we take a look at the graph of the function, just to be very exhaustive, we see that we have cosine of pi x, this is 0, and 1/6 is probably right about here. We can actually take a look at this on a different interval here. So 1/6 is the same thing as, I believe, 0.1666 repeating, right? So here we have 1, and here we have the value of 1/6, which is less than that. Should be just about square root 3 over 2 if I use my calculator. Square root 3 over 2. I have 0.866 roughly, and that's about 0.866, somewhere in there, right? That's about what I see right there. But if I look at this on a larger scale, to x max, I don't know, of 10 or so, right? I see I get a tangent line at 0, right? Or a horizontal tangent line that could approximate this at 0. I get a horizontal tangent line that could approximate this at the rate of change at 1, and one that occurs at 2, and one that occurs at 4, and one that occurs at 5, and 6, and 7, and 8, and 9, and 10. If I zoom out a little bit on this, so I make this, instead of -1, let's say negative 1.2 and 1.2 there, right? Decrease it a little bit and plot 1 and plot -1, right? I see these horizontal tangent lines go through the function exactly at integer values of x, right? Right at 5, right at 3, right at 1, right at 2, 4, 6, 8, and so on. So that just confirms some of the results that we had achieved. So that is number, let's see, what was that? 35. Oh, no, wait. 33. I apologize, 33.